Okay, let's give a few definitions before we enter into a great chapter, which is graph searching. So let's begin. What is a path in a graph? Well, if we have an undirected graph, like the one shown on display, we have a path, let's say, between two nodes, for example, 5 and 8. If we can find a sequence of nodes going from node 5 to node 8 and connecting them. For example, one such path will be this. From 5, we go to 2. From 2, we go to 3. From 3, we go to 8. So this is one path. It would be 5, 2, 3, 8. But then we could have another path, a different path, connecting the same two nodes. For example, from 5 we could go to 4, and from 4 to 2, to 1, to 3, to 7, and to 8. That's another path, going from 5 to 8. So from 5 to 4, to 2, to 1, to 3, to 7, and to 8. Much longer than the other one, but path nevertheless. Or we could have even these kinds of paths. Let's say from 5, we go to 3, we go to 1, we go to 2, we go to 3, we go to 1, we go to 2 again, we go to 3, and finally to 8. This is a strange path, but a path nevertheless. So we went from 5 to 3, to 1, to 2, to 3, to 1, to 2, to 3, and to 8. So the definition of path can be seen up here. So just a sequence of nodes, and we might give it a name. This might be P1, path 1, path 2, path 3, in which each of the nodes appear consecutively, and each consecutive pair is joined by an edge in the set of edges, containing the set of edges. So this happens for all the nodes, for all the paths, all the nodes in the paths we have studied. For example, there's indeed between these two consecutive values, or two consecutive nodes, we do have an edge between 5 and 2. Also, we have an edge between 2 and 3, and we have an edge between 3 and 8, and this pairwise consecutive relation is what defines a path. Being in one given node, we can always go to the next one, know where we have come from, and where we will go in the next time in the path. Okay, so that's a path. Now, a path, there are different kinds of paths. A path is simple if all nodes are distinct. For example, like the one we have said, this one, from 5 to 2 to 3 to 8, is distinct because none of these consecutive nodes appear more than once. But this other path, one in which we probably visit a group of nodes more than once, like 5, 2, 3, 1, 2, 3, 8. In this case, this is a simple path, and this is not simple. Because this node is not distinct. This node is the same as this other one. So, and the 3, the same as this one. So this is not a simple path. And in an undirected graph, undirected graphs may have a property of being connected if for every pair of nodes U and V, there is a path between U and V. Okay, so for example, in this case, is there a is this graph connected? Well, this graph is not connected. Why? Because we can find at least one pair of nodes, for example, 3 and 12, and there is no edge between 3 and 12. Between 3 and 12. Okay. So it is not connected, because being connected requires that this path property, the existence of a path, is valid for every pair of nodes. And this word, every pair, implies a universal quantifier. So if then remember that the negation of a universal statement is an existential statement. There is at least one. So if we negate the definition of a connected graph, the definition of a not connected graph is one in which there is at least one pair which is not connected, with no path between them. And one is enough because of this existential statement, okay, because of this existential quantifier. So we find at least one counterexample, we know that it is not connected. In this case, the answer would be yes. It is not connected, and the counterexample is this one. There is no edge between nodes 3 and 12. Now, a cycle, notice, let's define a cycle, is a sequence of nodes, so a path, but with a particular property that the beginning and the end of the path are the same node. So the first and the last, except the first and the last, all nodes are distinct. Okay, so, for example, this would be a cycle going from let's choose a color, going from 1 to 2 to 4 to 5 to 3 and to 1, back to 1. This is a cycle. We may find some other cycles, for example, between 3, 7, 8, and back to 3. Or an even bigger cycle. So from 6 to 5 to 4 to 2 to 1 to 3 to 5 and back to 6. This would contain actually the red one will be 2 cycles according to this, well, a cycle within a cycle. So we would have 6 to 5 to 4 to 2 to 1 to 3 to 5 to 6. But we have 6 and 6, and we have also 5 and 5. So this is a cycle, and within another cycle. It's a complicated cycle. An undirected graph is called a tree if it's connected and does not contain a cycle. Okay, like this one. You can find a path between any 2 nodes, but and there are no cycles. So we can define this particular kind of graphs by these 2 conditions. Connected, notice the AND operator, no cycle. So connected and no cycle. Connected is already a universal property, meaning that it's a property that holds for all vertices. There is a path between any 2 vertices and does not have a cycle. Okay, so that is a tree. Now, if we have a tree like this one, we might find several properties in the tree. It's easy to find some properties of the tree. Let's say if we have a tree with nodes, okay, we have a tree, this has actually 9 nodes. has 1, 2, 3, 4, 5, 6, 7, 8 edges. And this property generalizes. If we have n nodes, it will have n minus 1 edges, always one less than the number of nodes. And why would that be? Well, imagine that this can be seen in many different ways. One of these I will tell you right now. Imagine that we take a particular node, can be whatever node. For example, let's take node number 2, and let's promote this node and somehow move and shake the tree until we get it to have node number 2 at the top, and preserving the connectivity relations, so all the edges go to the same nodes. We do not change anything. It's essentially the same graph, the same tree. And we have 2 was joined to 3 here, and in fact we might do better. Join is connected to 3. 2 is joined to 3. 2 is joined to 4. And also 2 is joined to 1, and 1 is connected to 5 and 7, and 5 is connected to 6, and then 7 is connected to 8 and 9. Now that we have this kind of tree, we can see, we can make the following relation evident. So let's call those who are above one particular node, a node that is in a higher level than a given node. Let's call that the parent. So in this case, 7 is the parent. 7 is the parent, and 9 is called the child. So all relations, all edges define now a child-parent relationship. And it turns out that we have only one parent for each child. So one observation would be there's one parent for each child. Exactly one, except the node at the top, which we will call the root. The root node is node number 2. This is the only node that has no parent. Other than that, all other nodes have a parent. And having a parent means that there is a line or an edge between parent and child. So there's an edge between a parent and child, and we have n nodes in the whole graph, but only n-1 have a parent. That means that there are only n-1 edges. One way to see that. So edges, trees have several important properties which are sometimes easy to find or easy to observe or easy to prove, like this one. Okay, then, so we have proved, in fact, this proposition. But if G is an undirected graph on any nodes, any two of the following statements imply the third. For example, that G is connected and G has no cycles, then G has n-1 edges. We just proved, if we call this property A, this B, and this C, we just proved in the previous slide that A and B imply C. But we would have to prove also that A implies A and C imply B, and that B and C imply A. Rooted trees. Well, I have already defined that. And the same tree can be depicted in several ways, like in this case, these are equivalent ways. And a tree is a hierarchical tree if it has a root and all nodes are displayed in levels, as in this one. And we have the same relationship between each edge has one parent in one side, in one end, and a child in the other end. And that happens for all edges. And all nodes have a parent except the root node. And this is useful to model some hierarchical structures, such as phylogeny trees, which explain the evolutionary history of species, or just describes it. So we see which species are more related than others. And we see that mammals and birds are more related than, for example, birds and gut bacteria. Because there are several more steps between one another. We also use this kind of hierarchical trees to display some containment hierarchy in a GUI, in a graphical user interface, like in Java. So we have these elements that are called JPanels, JText fields, JSliders, and we have that, for example, a JSlider is contained within a JPanel, and a JPanel might be contained within a conversion panel or another JPanel. And this would be contained in another JPanel called a custom content panel until a JFrame. And these other two would be contained only to this panel. And this panel is contained in another panel, so on. We can easily depict the relationship of containment in a graphical user interface. And now it's time to go to graph traversal. This is one of the most interesting problems in graphs. And sometimes we might be given a graph, and we have to find out if it is connected. Okay? So we may want to solve problems like this one. If we are given two nodes, S and T, is there a path between S and T? Okay, we know how we can find that. Or we saw how to solve this in any of the graph representations, and we know that in an adjacency matrix, answering this question takes about constant time.